Hi, my name is Mohamad Aminul bin Azhar.
Hi, my name is Muhammad Danish bin Muhammad Hamidi.
Hi, my name is Danial bin Naser.
Hi everyone, this is Jia Yi.
And my name is Aufa Uzma Binti Irwan Syuhada.
First, let me briefly summarize the objective of this project. The main goal of this study is to analyze and understand the process flow diagram, PFD, for acetone production. This helps us apply chemical engineering and fluid mechanics principle while ensuring process efficiency and safety. Next, we visualize material flow, including raw materials, intermediates, and final products. Key engineering concepts like mass and energy balances, reaction kinetics, and separation techniques were applied. We also considered fluid mechanics aspects such as flow rates, pressure drops, and pump efficiency. Additionally, we performed calculations to reinforce our understanding of the process. From this study, we designed a detailed PFD, identified essential unit operations like reactors and distillation columns, and evaluated process efficiency through mass and energy analysis. This project provides a structured approach to understanding acetone production, optimizing efficiency, and improving process sustainability.
So now I'm gonna give introduction for principles of chemical engineering. So process flow diagrams or PFDs visually represents material flow, units operations, and process interactions. In this case, acetone production involves multiple input and output streams. There are two types of process. Number one is reactive process, which is isopropyl alcohol (IPA) converted to acetone and hydrogens that is controlled under conditions like temperature, pressure, and catalyst. Second one is non-reactive process, which is distillation, filtration, and heat exchange that used for separation and purification. For mass balance of reactive process, chemical reaction transforms IPA into new substances like hydrogen and acetones. There also occurs breaks and forms new chemical bonds in this chemical reaction. Both processes work together efficiently, and the PFD illustrates their integration within the production system.
Next, this is the process flow diagram and its description. First, we have two pumps which represent P401 and P402. Next, we have one feed vaporizer which represent E402, cooler represent E401, acetone condenser E403, reboiler E404, reactor R401, separator V401, scrubber T402, distillation column D401, and storage tank represent T401.
Okay, right now I'm gonna explain the mass balance on non-reactive system. So for the separator column, it has an input and output. The input consists of F1, which has the value of 326.1 kmol per hour, and the output is F2 and F3, which are the vapor stream for F2 and F3 for the liquid stream. For the overall mass balance is input is equals to output, and for the component mass balance we can compare it with hydrogen to find the liquid and vapor stream. To find the molar flow rate in all streams is by taking the actual molar flow rate, which is the 326.1 kmol per hour, times with the mole fraction in the plant flow diagram just now. This is also the same calculation step as the molar flow rate for the feed 1 just now. Right now I'm displaying the table for the molar flow rate on non-reactive system for all of the stream. To find mass flow rate, it is equals to the molar flow rate. We times it with the molecular weight of each component given. So these are the tables for mass fraction on non-reactive system. So the formula is mass composition is equals to the mass flow rate of component divided with total mass flow rate. So now I'm going to talk about the energy balance on non-reactive system. The first thing to do is by assuming our reference point. So for acetone, isopropyl and water has the same liquid state, but for hydrogen has a vapor or gas state, and for each of the component all has the same temperature and atmospheric pressure, which is 65 degrees Celsius and 1 atmospheric pressure. So for H1, H2 and H3 and H4 is equals to 0 because it is our reference state. For the other enthalpy, specific enthalpy is by using important appendix and by referencing the NSIT webbook from Google. And these are the table values for energy balance on non-reactive system. Next is the mass balance on a reactive system. So we use our reactor column as a unit. So we need to assume that 73.74% of isopropyl alcohol is consumed. By that, we can find the consume of other components and the generation of other components too. So this is the tables for molar flow rate on reactive system. So the mass flow rate value is equals to the molar flow rate times with molecular weight, same as the non-reactive system. And lastly, for mass fraction on reactive system is equals to the mass flow rate of component divided with total mass flow rate. So these are the tables for the reactive system.
So let me explain about energy balance on reactive systems. So this is the block diagram for the energy balance on reactive systems. This is the reaction equations and this is the calculations. So basically we're using the same calculation on how we want to calculate the non-reactive, but the difference is we have to find the extensives of the reactions.
Today, I would like to discuss how fluid mechanics play a key role in acetone productions by optimizing flow rate, pressures, and heat or mass transfer to improve efficiency and sustainability. By applying Pascal's law, Bernoulli equations, and Reynolds number, we can ensure proper mixings, pressure balance, and heat transfer. It's crucial for feeding isopropyl alcohol into reactors and distilling acetone. So let's explore how these principles enhance yields, reduce waste, and improve sustainability.
For piping details, we have 11 pipes. For P1 and P2, we use the same type of pipe, which is stainless steel 2-inch schedule 40. For P3, the section is scrubber. The stream is from scrubber to vent. The type of pipe is stainless steel 3-inch schedule 40. For P4 to P11, we use the same type of pipe, which is stainless steel 3-inch and schedule 40, and also the same internal diameter, which is 0.0779.
Now, let's go through the pressure drop calculation step by step. First, we calculate the volumetric flow rate using the mass flow rate that we determined at chapter 1 by dividing by the fluid's density. Next, we determine the velocity of the fluid using the volumetric flow rate and pipe dimensions. Then, we calculate the Reynolds number to check if the flow is laminar or turbulent. Based on our calculation, we need to find the friction factor using an equation for turbulent flow. With the friction factor, we determine the total frictional loss considering the pipe length, fittings, and sudden changes in flow direction. Finally, we use Bernoulli's equation to calculate the pressure drop, which tells us how much energy is lost due to friction and resistance in the system. This is an example for a pipe that contains a pump. So we just do the same steps. Since a pump is present, we calculate the work done by the pump using efficiency and power equations. Finally, applying Bernoulli's equation, we include the pump's contribution to the energy balance and determine the pressure drop, which reflects energy changes due to friction and pumping effects. These steps apply to other pipes too, with different values based on flow, pipe size, and fluid properties. These are the summary of our pressure drop in each pipelines. Note that P2, P3, P9 and P11 is a vapor streams.
So let us continue with the last part of fluid mechanics, which is strategy for delivering main product. So basically, we are using pumps to flow and maintain continuous control flow of isopropyl (IPA). And we are using Bernoulli equations and fluid dynamic principle to ensure smooth and efficient transportation of IPA. And this is the storage tank properties. This is the justifications of the materials. So this is the word of arm, the assumptions, schedule 40 stainless steel pipes, horizontal pipeline, and etc. So this is the calculation. We have to count mass flow rates, volumetric flow rates, mean flow rates, Reynolds number, friction factor. After we count all of this using the assumptions and the information, after all that, we can count the work of pump.
To conclude everything, fluid mechanics is essential in acetone production, ensuring smooth flow, pressure control, and efficient separation. By applying principles like Bernoulli's equation and pressure drop calculations, we optimize flow rates and key processes like distillations and reactions. Chemical engineering concepts, including reaction engineering and separation techniques, work together to improve acetone yield, purity, and efficiency. Proper fluid and process management help reduce energy losses, prevent backflow, and enhance product quality, showing the strong connection between fluid mechanics and process optimization.